Hello students, and welcome to this next edition in our revision series of lectures. So we will continue with the topic of revision of work by energy and circular motion today. So let's begin. So the first concept in this particular section, work by energy, was the concept of work done by a force. So as we had seen, the general definition of work done by the force was integration of F dot ds. Okay, so if a force F is acting on a particular particle while it is excuse me, making a displacement from some initial position, let's say A, to this final position B along this kind of path, then at any instant in between the displacement, in between the total journey from A to B, if the instantaneous value of force is F and the displacement during a small interval of time is ds, then the work done by instantaneous force for this differential displacement ds is F dot ds. Therefore, total work done, say from A to B, that becomes the integrated sum along the path. And that is why we say that work done is equal to the path integration of F like this. Okay. However, the very important special case over here that comes into play is that what if the force is constant, that is the magnitude and the direction of the force is constant. In that case, this definition of path integration reduces to a simple dot product of force with displacement. So the important exception to remember over here, that if F is a constant force, that is both magnitude and direction are constant, then this path integration simply reduces to the scalar product of force and displacement. And of course, we had seen that work done is a scalar quantity expressed in joules, SI unit being joules, where 1 joule is equal to 1 Newton meter. So this was the basic concept. So let's do some revision questions based on the definition of work done by a force itself. So let's start with this example. Body is placed on a smooth surface. Now, initially, the coordinate of this is x equal to 1. And we start applying a force on it like this, where we are defining the horizontal axis as our x-axis. So a horizontal force along the x-axis such that its magnitude F is equal to k root x starts acting on the block initially at x equal to 1. So find the work done by this force as the block moves from x equal to 1. This x is in meters, okay, to x equal to 25 meters. Okay, given k is 20 newtons per meter to the power half. Okay, so let's understand here. So this is a case where the force is variable, so we will have to use this path integration method. Okay, but it's a one-dimensional situation. The force is along the x-axis, okay, and the displacement that is happening, that's also along the x-axis. So okay, so this f dot ds will be reduced with k root x dx. So this work done becomes integration of k root x dx from the initial position, which is x equal to 1, to the final position, which is x equal to 25. So as you can see, and k's value itself was 20. So 2 by 3 into 20 into this will become 125 minus 1. So this value in joules will be equal to the work done. Okay. So just make sure you're clear with all the steps over here. We'll move on to another question next. Okay, so this is an example of the usage of integration to calculate work done by a variable force. Okay. Now next up, let's look at this situation. So we have a 37-degree rough inclined plane. The coefficient of friction here is 0.2. And we have a block of mass 5 kilograms, which is released from rest from the position A. We take the value of G to be 10 meters per second square. Okay, so this block is released from this position. Now, after some time, it has slid and reached this position B. So it has slid through a displacement of, let us say, 15 meters. And therefore, by the time it's reached V, it has some speed V. So we have to find the work done by all forces acting on the block from A to B. And show that half mv square, that is its kinetic energy at B, equals to the net work done. Okay, so so let's try out this question next. Okay, so let's look at this question in detail. So we can see as the block is sliding down the inclined plane, there are three forces in total which are acting on the block, all of which are constant because it's moving along a straight line path. So the gravitational force acting on it, the normal reaction force acting on it, and the frictional force acting on it, kinetic friction, they will all be constant forces. And we can see that normal reaction will be equal to mg cos 37 . So we're taking the mass to be 5 kilograms. So this will become 40 newtons in magnitude. And the kinetic friction mu n will become mu mg cos 37. So that will become 0.2 into 40. That is 8 newtons. Okay, now we can see that because mg is 50 newtons. Now we can see the displacement of the block is down the inclined plane. So its direction is like this. It's 15 meters in magnitude as the block goes from the position A to the position B. So you can see that work done by mg will be equal to okay because this angle here, you can see this angle is 53 degrees. So that is 450 joules. So this is the work done by the gravitational force. Work done by normal reaction will become zero because normal reaction is perpendicular to the displacement here. And work done by friction will become minus of friction into displacement because kinetic friction acts at 180 degrees with respect to the displacement. So we can see that that is minus of 8 into 15. That's a minus of 120 joules. So this becomes the answer of the first part. Okay, the work done by each of the forces you can see is this much. Okay, so hope this part is clear to each and every one of you. Okay, so once this is clear, next let's understand the net work done here. That will become the sum of work done by mg plus the work done by normal reaction plus the work done by friction, which we saw is this much. So 330 joules is the net work done. Okay. Now we can show from Newton's laws that the acceleration of the body as it slides down the inclined plane is mg sine theta minus kinetic friction divided by m, which is this. Taking the value of theta as 37 and mu as 0.2. So this is the acceleration. So we can also show from kinematics that if the body starts from rest at the point A, then by the time it reaches the point B, which is at a displacement of 15 meters, B square will become 2as. So 2 into 4.4 into 15. Okay, so that will become how much? 30 into 4.4 or so V will become square root of 132. Okay. Therefore, its kinetic energy will be 330 joules. So that verifies that the net work done by the forces acting on it is equal to the value of half mv square, which is the kinetic energy at the point B. So of course, you know, this should always happen in this case because we have the theorem that the net work done by all the forces acting on the body equals to the change in its kinetic energy. So the relationship between net work done and kinetic energy, that is just getting verified over here, that the net work done equals to the change in kinetic energy. So in this case, that is the kinetic energy at B minus the kinetic energy at A. That's why we were getting the net work done equal to half mv square. This relationship here being the work kinetic energy relation. Okay, which later of course leads to the work energy theorem as you know it. So hope this example is clear to everyone. Now next, moving on, we will discuss about conservative and non-conservative forces once more. Okay. So this is a very important concept and definition. So let's just revise about it thoroughly once. Okay. So we had seen that definition of conservative force is a force such that if the work done by a force is path independent, that is depends only on position and not on the path from one position to another, then it is called a conservative force. Okay. And the work done in a round trip or closed loop path by a conservative force must always be zero. So this is an important concept here. Whereas if the work done is path dependent, then it is non-conservative by definition. And obviously work done in a closed loop path or a round trip will be non-zero by such a force. So this was the definition of conservative and non-conservative forces. So for example, any constant force is conservative. Because for a constant force, we saw that work done is F dot S. So by definition, this is path independent. Then another example is spring force. The restorative force by a spring is conservative, because as you can see, whether we are extending a spring or compressing a spring, the work done by it, suppose a spring is being extended like this, then the work done by the spring force is like this. So that becomes integration minus kx dx. Or even if we are compressing the spring in a situation where this spring of constant k might be in a compressed state. So its length is L minus x, L being the natural length. So it would be applying a spring force or a tensional force like this, while let's say the displacement is happening like this. So whether we are taking the first picture or the second picture, the work done by the spring will be given by this relation. So from whatever initial to final. So we can see that work done by the spring is minus half k into final x square minus initial x square. So as you can see, this expression is independent of path. This is path independent, because it depends only on final and initial position. That shows that the spring force is also an example of a conservative force, just like any constant force is conservative. Okay, and we will continue to see more examples of conservative forces, including central force, which is a very important type of force. Okay. But next, if we look at kinetic friction, that's a good example of a non-conservative force. Non-conservative in nature. Simple way of understanding that is, suppose we have a rough surface which has a coefficient of friction mu, and we have placed a block of mass m on it initially at this position A. Now suppose we take it from the position A to the position B directly by pushing it with some external force like this, okay, where this distance is L, and also suppose another position of it is C, where this distance is L by 2. Okay. So first case, if we look at work done by friction from A to B directly, okay, you will see that work done will be minus mu mg into L, because we are pushing it with a horizontal force. So the normal reaction acting on this will be equal to mg. So if it is moving in this direction, then the frictional force acting on it will be this much, and it will be umg. Okay, so but suppose you want to calculate work done by friction from A to B to C. Okay, that is, and then back to. So this is a path such that the initial position is A and the final position is B, but it's not directly from A to B. So what will happen is that during this, the work done by friction will be work done by friction from A to C first, and then from C back to B. Now what will happen is that when you're going from A to C, the work done will be minus mu mg into 3L by 2, because you're making a displacement of 3L by 2 from A to C. And then when coming back from C to B, the direction of friction will reverse, but so will the direction of displacement. So this will again become minus mu mg, but into L by 2. So you can see that this is becoming minus 2 times mu mg L. This is the work done by friction. Now if you compare this expression with this expression, you can see that in both cases, the work done by friction from initial position A to final position B is different for two different paths. Okay. Hence, friction, kinetic friction in this case, is non-conservative. It is different for the two different paths. It shows you that the work done by friction is path dependent in nature. It is not path independent. Therefore, it is a non-conservative force. Okay, so let's move on with an example of a more complex two-dimensional type of force, and let's see how we can determine the nature of the force, whether it is conservative or non-conservative. So next example, a particle moves in the xy plane and is acted upon by a variable force given by this particular relation at the position xy, where x is in meters, y is in meters, and this force is in newtons. So this particle is being acted upon by this kind of a variable force. Now in our xy plane, in our coordinate frame, let us say we are considering the motion of the particle from the origin to this particular point, which has coordinates 4, 4. Okay. But we are taking, in one case, we are taking a direct path from here to here, and another case, we are taking an indirect path. Like this. Okay. So we have two different paths. This is path 1, and this is path 2. So the particle moves from the origin to the point P as shown. So we have to find the work done by this force F for path 1. Find the work done for path 2 and see to show that this force is conservative. Okay, we have to prove that the force is conservative. So just take a minute or so to try out this question we will discuss. So if we are taking this particle on this first path 1, okay, how we will calculate the work done by this variable force. This is how this force was given. Now, what we are doing in this case is first we are going from the point origin along the x-axis. We are going to this point here. So let's say this point is some q. So its coordinate will become 4, 0. And then we are going from q to p parallel to the y-axis from y equal to 0 to y equal to 4 meters. Okay. So this total thing is the path 1. Okay. So this work done will be equal to work done from O to Q plus work done from Q to P. Now let's first start by understanding the work done from O to Q. So for that we have to do this F dot integration, F dot ds from O to Q. So now while going along this path, you can see at any intermediate point here, the coordinate of the particle is x comma 0. So if you substitute x comma 0 on that force, we will get a force of 2x I cap. Okay. And the displacement is happening like this along the x-axis. So we'll get the displacement as dx I cap. So this work done will become 2x dx. So next we will substitute this here. So this becomes 2x dx from x equal to 0 to x equal to 4. So you can see that this becomes x square from 0 to 4. So this becomes 16 joules. So this is the work done from O to Q. Okay. So just make sure you understand this step here. Then we will calculate the work done from Q to P next. Okay, now next going from the point Q to P. Okay, so again, let us consider we are at a general point like this. So our coordinate will be, x coordinate will be 4, y coordinate will be y, and we are moving along the y-axis. So our displacement will be dy in that direction. Okay, so at that particular point, we can see that the force will become 2x. So that is 8 I cap plus 2 plus y square j cap, and the displacement will be dy j cap. Okay, so f dot ds will become like this. Okay, so the work done from q to p will be integration f dot ds from q to p. So that here will become 2 plus y square dy integrated from y equal to 0 to y equal to 4. So that work done, you can see, will become this. This will be the work done from q to p. So the net work done for path 1 becomes this much. Okay, so this is the net work done. Okay, so now let's understand the work done in the second path. That is a direct path from P to Q. Now this part of the question is a little bit more tricky because we'll have to use the equation of the straight line itself, which is the direct path from the point O, which was the origin, to the point P, which is point 4, 4. So now we are talking about this straight line. So this is the path we are talking about. This is our path 2. Now you can see that this is a straight line which has a slope of 1. So this slope is 1. So the equation of the line, path 2, is along the line y equal to x, because it's passing through the origin having a slope of 1. So therefore, any point on this line, so at the point xy on this line, y is equal to x. Okay. So the force, which is 2x I cap plus 2 plus y square j cap, this can be written as 2x I cap plus 2 plus x square j cap, because y is equal to x. And anywhere on this line. and therefore the displacement, which is like this, can be written like this, because y equal to x means dx is equal to dy. So along this particular path, we can reduce the expression for work done as the dot product of these two things. So this is the total work done that we are getting for path 2. Now, interestingly, you can see that it's equal to the work done that we had got in path 1. Okay, so just make sure you're clear about that point. So make sure you've understood the steps in this particular calculation here. Then we'll come to the third part where we have to demonstrate that this particular force is conservative. That means the work done should be independent of path. So in a sense, we have already done that demonstration because we've shown that for these two paths, the work done is the same. However, we have to generalize that now. We have to show that it's not just for these two paths that is the same, but if we take any path between any two particular points, then the work done is independent of the path and depends only on the initial and final position. Okay, so let's come to the third part where we have to show that the work done is independent of path. So this is where the question gets very interesting. So the nature of the force is such that even though it's variable, we'll be able to demonstrate that the work done is independent of path between any two given points. So if we now visualize a general sort of situation, not necessarily only from the origin to the point P, and not necessarily a straight line path, but any arbitrary kind of path, any randomly selected kind of path. So from any initial position A to any final position B, let's say we are taking any kind of random path. So we have to show that the work done is independent of the path. To show that the work done only depends on the coordinates of A and the coordinates of B, which are, let's say, like this. Okay. So if at any point the force is like this, okay, and the displacement is like this, so you already know that the force is given by this expression. Okay. And the displacement will be some general value having an x component and a y component, the differential displacement. So work done should be f dot ds from initial position A to final position B. So when we do this dot product, it becomes 2x dx plus 2 plus y square dy from x1 y1 to x2 y2. So we can see that we can split this into two integrals and just conduct the integrals out separately like this. So you can see that irrespective of what the path is, okay, any path from A to B will give us the same answer for the work done from the point A to the work done to the point B, which will be x square from x1 to x2 plus 2y plus y cube by 3 from y1 to y2. So you can see that this expression is independent of path. Okay. So you can see that the expression for work done is path independent because it depends only on the initial and final position. Okay. So this demonstrates that the force is conservative. Okay. So this all demonstrates that therefore this particular force is a conservative force. All right, so having understood this, the next thing in this concept set was concept of potential energy and its relation with internal conservative force. In a system. So we saw that if we have a mechanical system wherein the internal force is conservative in nature, for example, a spring mass system where the internal force is the spring force, the restorative force applied by the spring, which we already understood is conservative, or we consider the earth plus a body which is being moved around as a system. And we know the gravitational force applied by the earth on the body is a conservative force. So it becomes an internal conservative force. So we saw that we can define the change in potential energy. A potential energy we generally denote with the symbol U as negative of the work done by the internal conservative force. Okay. So for example, we have the work done by a spring force in general we had seen was integration minus kx dx from initial to final. Therefore, change in potential energy of a spring will become negative of work done by the spring force. So it becomes integration kx dx from initial to final. So delta U for a spring becomes defined as half k final position square minus initial position square. And from this, we define the absolute potential energy of a spring as half kx square. So where this formula was coming from this general relationship between potential energy and internal conservative force. Similarly, we see that for a body of mass m, okay, on or near the Earth's surface, that is, the height is very small compared to the radius of the Earth. We can say that the work done by gravitational force is mg dot s. So that becomes minus mg delta y, where delta y is the vertical component of displacement. Okay, so if the body is making a displacement like this, the vertical component of that is delta y, and the horizontal component is delta x. Gravity is acting along the negative y-axis. So taking that into account, so the change in gravitational potential energy is negative of work done by gravity. So it becomes mg delta y. So this is the relation that we have. Gravitational potential energy changes by a factor of mg delta y when a body of mass m is given a vertical displacement of delta y. So these two become the important formulae within mechanical systems. Okay. And having understood this formulae, we come to the general work energy theorem, which was the main application part in this chapter. That is, the work done by any external forces acting on a system plus the non-conservative forces acting on the system equals to the change in kinetic energy plus the change in potential energy of the system. Okay. Now also we have, in the case of a mechanically isolated system, the work done by external forces is also absent and there are no non-conservative forces. So work done is zero. So change in kinetic energy plus change in potential energy is zero. Or we can say that the sum of kinetic energy plus potential energy is constant. So this situation, when we have a mechanically isolated system, this situation is called the conservation of mechanical energy. Because the sum of potential energy and kinetic energy is called the mechanical energy of the system. So let us look at an example or two of this situation. Okay, so let's take this to be a smooth surface. Now, we have a block of mass m which is attached by an ideal spring of constant k over here like this. Okay. Now, the block attached by the spring is released from rest such that x is equal to 0 for the spring. That is, the spring is relaxed. So first of all, find the block's speed v as a function of x, that is the extension of the spring. Okay. And from this, we will also find out the maximum extension of the spring and we will find out the maximum speed of the block. So realize here that when we release the block from this kind of position, it will oscillate because we are releasing it from rest. So with the spring in relaxed state initially, so mg sine theta acting on the block will make it accelerate, but as it accelerates, it pulls the spring. So eventually the spring pulls it back. So it will accelerate, then decelerate because of the spring force, then come to rest. Then at the point where it comes to rest, the spring force is dominant, so it will again slide up the incline, coming all the way back to where it started from. So it will be oscillating up and down. Okay, so it will have a maximum displacement every time it reaches the other side, coming to rest. And in between, it will have a maximum velocity or maximum speed at some point of time. So both of these we have to calculate over here. Okay, okay, so let's check out. So what's happening is that if we compare this situation from the initial state like this, where the spring was at natural length. So x is equal to 0 for the spring and initial speed of the block is 0. So after some time, the block has, let's say, reached here. So the spring has got extended. And by now the block has got a speed v. Okay. So going from this first position to this second position, you can see that if you take the block plus the spring plus the earth as your system, then you can see that on the block, the spring force and the gravitational force, these are both internal conservative forces. Okay. And the normal reaction will anyway be doing zero work and friction is absent. Work done by normal reaction will be zero because n dot s will be zero. So we'll have the relation that change in kinetic energy plus change in gravitational potential energy plus change in elastic potential energy of the spring should be zero. Okay. So for going from this state A to this state B over here, let's say, So A to B, you can see that going from A to B, we can see that the change in kinetic energy is plus half mv square. The change in gravitational potential energy will be minus mgh, let's say, because the block is having a vertically downward displacement. So I'm just showing it on the side as it goes from here to here. This displacement is x. So the block is having a vertical component of displacement of h downwards. So delta y is minus h, which will become minus x sine theta. So we'll use that over here. Okay. Plus the spring's potential energy is becoming half kx square. Initially it was 0. So we have this relation. So substituting the value of h here as x sine theta, we'll have half mv square is equal to mgx sine theta minus half kx square. Or we can substitute v as square root of 2gx sine theta minus k by m x square. So this becomes the answer to our first part. This is the speed v as a function of x. Okay, so this is the application of the work energy theorem. In this case, it becomes conservation of mechanical energy. Okay, so next up, we can see that from this, we can easily calculate the maximum extension. So you can see that for maximum extension of the spring, the block should come to rest momentarily when x is maximum. It is oscillating up and down. So at the lowest position, it starts from rest over here, initially accelerating down the inclined plane, but eventually decelerating, and at some stage coming to rest. So that is when the extension is maximum. So this and this are the extreme positions. So this will give us the solution x equal to 0, which is obviously the initial case, or x equal to 2 mg sine theta by k. So this is the maximum or the maxima of x. So that becomes the answer to our second part. Okay, and for the third part, you can see that we want to find the maximum speed. So there are two ways we can understand this. One is dynamically, that initially the block is accelerating, then after some time the block starts decelerating. This happens when kx becomes greater than mg sine theta, whereas this is initially when kx is less than mg sine theta. Okay. So in between it will reach the maximum speed at the position where acceleration is 0. The speed will be maximum. Okay. So that's basically the equilibrium position. That's one way we can understand it dynamically. Or another way we can understand it is that the kinetic energy half mv square was this kind of a relation. It was mg x sine theta minus half kx square. So you can see that this kinetic energy is a sort of quadratic function. It's like some alpha x minus beta x square, where alpha and beta are constants. So if you plot the kinetic energy versus the extension of the spring, you can see that you are getting this kind of a parabolic graph, where this is x maximum, where v becomes 0. So here is where the kinetic energy is maximum at half of x maximum. So you can see from this also. So whether you go by this method, so v is maximum at equilibrium point. So that is where mg sine theta should be balanced by kx, or x should be this. Okay. Or you go by this. Now we had already calculated x max in the last part. That was 2 times mg sine theta by k. So whether you go by the graphical method or the function method, or by the logical method where you understand dynamically that the acceleration should be momentarily 0 at the point where the kinetic energy is maximum, come to the same conclusion. So we will substitute this in the kinetic energy versus x relation. So half mv square this. So substituting this over here, we get this. That will give us v max as I'll just minimize this part. You can go through this once. So this kind of analysis becomes very important in our application of conservation of energy or in general work energy theorem. So make sure you understand this, and with this we conclude today's session. So wish you all the best, people. So in the next session, we'll pick up some more examples of application of work energy.